Okay, so now we're going to turn to reading. So in reading, we're entering the language system through the visual modality and specifically through the written word. And before we turn to brains, I want to just start by discussing some behavioral foundations. So what have we learned about reading from psychological research on reading? First, I just want to draw a distinction between language and reading, an important one. And that is that although language is universal in the sense that all humans have language, children automatically learn language if it's just in their environment, reading and writing are not like that. So of the roughly 7,000 languages in the world, about half of them are unwritten. So you can absolutely be a language and not have a writing system at all. And that's very common. And so children don't learn to read as naturally as they learn to speak or to use language, I should actually say here. And also a decent percentage of children have trouble reading. So about 20% of children have some level of reading difficulty. And then, a slightly smaller percentage of actual dyslexics. But this is not something that you can take for granted. So contrary to language, which doesn't need to be taught to children, reading and writing are very much taught skills. So that makes it very different from learning to use language otherwise. So when a child learns to read, so this is now I'm thinking about a child who is a native user of a spoken language as opposed to sign language. My example comes from spoken language. They have word representations in their brains that look something like this. So they have sound representations that are connected to meanings. So they've drawn these connections between sound form and meaning. And the connections are bidirectional because we both comprehend language, so we are able to take the sound stimulus and find the meaning that corresponds to that, or the meaning that's connected to that sound representation. And then, of course, we're also able to go in the other direction, so we're able to have a meaning in mind, or message in mind, a concept in mind, and then we're able to link that to the sound representation and externalize that. So that's sort of like let's just say, or you learn to read in kindergarten. This is, you come into the task of learning to read with this kind of representation in your head, and your task now, your brain's task, is to connect a new type of representation into these existing representations. So now we also have this orthographic representation of cat, that we need to be able to link up with the existing lexical representation. So how does that work? So it's quite intuitive that we are going to link that orthographic representation to the phonological representation. So there obviously, we can, in the English type orthography, there's a very clear relationship between the sound and the orthography. And, reading, when we're learning to read, we're very much learning that correspondence. And so here too, we have other types of evidence too, apart from that intuition, that this connection between sound and orthography has to exist. So it could, of course, be the case that we learn to connect cat to this representation by connecting that orthography to the meaning, and then it only connects to the sound through the meaning. That's a logically possible model. But we know that's wrong, because reading does not depend on meaning. So we're able to read phonological strings that don't connect to any meaning in the language at the moment, at least. So I can read "mied" without any problem, even though it is not an existing English word, as far as I know. And we can also go in the other direction. if you hear a phonological form that's a non-word, you're able to give it some kind of an orthography. So we're able to write non-words as well. So here, those two phenomena give us those two arrows between phonology and orthography, the sound representation and the written word. But now, do we also need an arrow between orthography and meaning? So is the orthographical representation also directly connected with the meaning representation? In order for us to read, that wouldn't have to be the case, right? So we could just learn to map the orthographic representations to the sound representations, and then because the sound representations are linked to the meaning, we're able to understand what we're reading. But it turns out that we have all sorts of evidence suggesting that actually the orthographic meaning does also have a direct link. The orthographic representation does also have a direct link to the meaning representation. In fact, in very fluent reading, so sort of silent reading, that is what happens. So you are sort of like accessing meaning directly off of the orthographic representation, while there is also sort of like ancillary spreading activation to the phonology. So we kind of know that the phonology is always active, but it seems like you also have a very fast route from orthography to meaning. Evidence for that link between orthography and meaning also comes from aphasia. So there are some aphasic patients or aphasic individuals who have an inability to name objects, so name them out loud. So if you get, say this picture of a cat, this type of a patient would not be able to then name that cat. So they can't say like, okay, cat, okay? So they can't go from meaning to sound. But the same kind of patient might be able to go from they might be able to write down the word. So that suggests that they're able to go from meaning to orthography, suggesting that the green arrow exists. And once they've done that, they can actually read the word. So then they can follow the other green arrow here down to phonology. So that gives us some evidence for a link from meaning to orthography. That's a direct link. What about the other direction? Well, here again, aphasia evidence is informative. So in aphasia, it's also possible to lose your ability to read aloud non-words. Okay, so when we're reading aloud non-words, we're using that connection from orthography to sound. And so if you can't do that, then it seems like that connection from orthography to sound is impaired. But these individuals can still be able to read existing words, even really complicated ones like chrysanthemum. I'm not even sure if I'm pronouncing that right. So it seems like whether that orthographic form links up with an existing meaning is the crucial bit for these patients. So it seems that they're able to go from that orthographic representation via the meaning to then the phonology. So it's a complicated way to read, but that seems to be what's happening with these individuals. So they also maintain good reading comprehension. Silent reading comprehension. So on the basis of evidence like this, we have come to believe in something like the triangle model of lexical representation, so that we really have your representation of a word in your brain is kind of this triangular connection between the sound representation, the meaning representation, and the orthographic representation. Okay, so how do our brains then read? Well, it's interesting to think about it in connection to our comprehension of auditory language. So when we're listening to language or hearing language, the auditory stimulus has an inherently serial character. So it comes to your ear kind of sound by sound. Okay, and that's how auditory perception works. It has this inherently serial nature because the stimulus has the serial nature. And so when we're reading, we can ask the question, well, do we read in a parallel way to that? So is the reading mechanism kind of very similar to the auditory perception mechanism? And if it is, then that suggests that maybe that kind of seriality is sort of an inherent property of language. It could be. Maybe the way that language has set up shop in our brains really demands that seriality. So in some sense, now that when we have the written text, which, you know, doesn't come letter by letter into your brain, we see big chunks of written text at once, and we're able to, you know, we can take it in whatever order we want. It's not an inherent property of the stimulus that it comes in serially. So we can ask this interesting question of whether we can, our brains are in some sense able to break away from the serial way of processing, or do we still kind of do it more or less serially? So do we read serially letter by letter? That's the question. And we don't do that, okay? So there's a very old argument against this type of processing, and that's the so-called word superiority effect. And the classic study by Reicher looks like this. So there are 3 different conditions. There's a word condition, so an existing word condition, letter condition, just one letter, and then a non-word condition that's a letter string that doesn't map onto a meaning. And the trial structure for each of these conditions is such that first there's a fixation point, then you get the word, letter, or non-word stimulus, and then you get a response display where you have to indicate which one of these letters occurred in the word. So it's a pretty easy task, okay? So here we get word, and then you have to say if it's a D or K. In the letter condition, you just get the letter, and then D or K, and then in the non-word condition, you get same task. Okay, so here, the serial letter by letter processing model would clearly predict that the letter condition should be the easiest because you only have one letter to deal with. That should be very easy for your brain to, you know, detect, and then in the task phase you can indicate which one you heard. Whereas in both in the word and the non-word conditions, there's just more units to go through, and that should make the task harder. But surprisingly, that's not the finding from this study and other studies like this. It is instead the word condition that is clearly the most accurate condition. So it seems to be the case that when that letter is actually embedded inside a word, it makes letter detection easier. And we think that that's because in the word condition, your brain has kind of 2 representations that give evidence for the presence of that letter or character. So your brain has stored a visual word form representation, and within that representation, you have evidence for the existence of D in this case. And then also kind of, you know, lower down in the processing stream, you have evidence that that was a D letter. And so there's these both word level and letter level evidence for the presence of that particular unit. So we don't read serially letter by letter. If we process words serially letter by letter, then processing a letter should be faster than processing a word. But it turns out that basic prediction is wrong. And so instead, most models of visual word recognition assume some type of parallel letter detection. So we're taking in the letters in a parallel fashion. Here's a classic model by Rayner and Polacek that illustrates one version of that. So you have a stimulus work. There's some kind of feature detectors that do lower level visual feature processing. Then that gives you a boost of activation at the letter level. So you get kind of activation for the the target letter. So here, for example, W is the actual correct match, but also visually similar letters will get some activation. And then from that, the activation will continue on to the word detector level. And again, you don't just get activation for the exact match, but other similar looking word forms will also get some activation. So now here, the model is spelled out for one specific instantiation of, say, the word work or these other words, and we're spelling it in the capital letters. But of course, we know that it can't be the case that the word detectors are in like some specific font or something like that. Our word form recognition system and our letter detection system operate on some kind of abstract representations that are able to abstract away from all that variance in the actual visual form. And it's a remarkably robust system. So we are really able to very quickly recognize, sort of, even if the form looks very unfamiliar. And we have some very striking experiments that show that changes in font or upper lower case, and actually even script, so some languages can be expressed in more than one script, really has very little or no effect on processing times. So the letter representations are extremely abstract in a way that's actually quite fascinating. So we read in a non-serial way, and as I was kind of priming you to think earlier, that actually teaches us something about language. So it teaches us that the seriality that's an inherent property of the sound stimulus and therefore of auditory perception is not an inherent property of language. So we are able to break away from it, at least to some extent. So the language system is able to receive the input in a more parallel fashion when the properties of the form representation allow it. So the written word is a visual percept that's sort of a static form, and we can take that in a more parallel way that than what we do in the auditory domain. So that's I think interesting. Okay, so from psychological research on reading, we've learned that the orthographic representations connect both to sound and meaning directly. And we've also learned that reading involves parallel letter detection, not serial letter by letter reading, that leads to activation of abstract word form representations. And next, we'll talk about what we've learned about the brain representation of word form representations and letters.